Okay, so let us do the alternating current numericals. Okay, so see in the PDF provided, the first problem, number 1, a resistor of resistance 100 ohm is connected to an AC source. Epsilon is 12 sine 250 pi t. Okay, clear? Find the energy dissipated as heat during t equal to 0 to t equal to 1 millisecond. Okay, clear? Fine. So here you have to do, so basically this is epsilon naught sine omega t, right? So epsilon naught is 12 volts and omega is 250 pi. So 2 pi f is 250 pi. So f will be 125 hertz. Okay, the frequency. Okay, then this will be the frequency. Anyway, what we have to do is the energy dissipated. So the energy dissipated will be certainly power PDT, power into time. Okay, from 0 to 1 millisecond, call it T. Okay, we'll later put the limit. Okay, so it will be epsilon square by r dt. Okay, so R resistance is given as, in this problem, as 100 ohm. Okay, so 1 by R is constant, taken out the integral. So it will be epsilon 0 square sine square omega t dt. Okay, from 0 to t. So it will be epsilon 0 square will be taken out. Now put 2r. Okay, so as I have multiplied the denominator by 2, we have to multiply the numerator by 2 as well. So we will have one minus cos 2 omega t dt. So now see, square by 2r, it will be 0 to t dt minus 0 to t cos 2 omega t dt. So it will be 0 to 2 dt is t minus, this is sine 2 omega t by 2 omega from 0 to t. It is t minus 0 is t. So it will be epsilon 0 square by 2r t minus 1 by 2 omega sine 2 omega t minus sine 0. I am not writing it now. Sine 0 is 0. So this. Now you see, omega is 250 pi, right? So if I put it here, 250 pi, so what I will get? Epsilon 0 is 12, so 12 square, 2 into 100. Now t is 1 millisecond, that means 10 to the power minus 3 seconds, minus 2 omega into sine 2 into 250 pi. Okay, pi, and t is 10 to the power minus 3. So you see what happens here. 144 by 200 minus 1 by 2 into 250 pi is 500 pi, and here it is 500 by 1000 is 1 by 2, so sine pi by 2, so it is 1, right? So ultimately we'll get 0.72 here, and here we will have if 10 to the power minus 3 is taken common, so what we get here, it is 1 minus and 2 by pi, right? It's like this. Okay, so 2 by pi is 2 by 3, that is 1 by 3. Okay, nearly 2 by 3, so 1 minus 2 by 3 is 1 by 3. Okay, so it is 0.24 into 10 to the power minus 3, so it will be like 2.4 into 10 to the power minus 4 joule. Okay, fine. Now let us do problem number 3. Problem number 3 is extremely important for the boards. Okay, extremely important problem. This type of problem is very much common in boards question. They ask you that an electric bulb is designed to consume 55 watt when operated at 110 volts. It is connected to 220 volt 50 hertz line through a choke coil in series. Choke coil means an inductor, right? What should be the inductance of the coil for which the bulb gets correct voltage? Okay. It may also say, in other words, that the bulb glows correctly. Okay, so you see, first this is the bulb, actually bulb is the resistance. Okay, so when it is connected to 110 volt, then so I get power is V square by R. So power is 55 watt. So it is 110 into 110 by R. So it will be 2. So R will be 2 into 110 is 220 ohms. Alright, clear? Acha. It is connected to a 220 volt 50 hertz line through a choke coil in series now. Okay. Now this bulb is connected to a choke coil, that is a choke coil of inductance L, and an AC source of 220 volt 50 hertz. The frequency is 50 hertz and the RMS voltage, always this is given as RMS. Okay, this is always given as RMS. Okay, this voltage, source voltage. Okay, alright. Now when this bulb is connected to this choke coil and the AC source, actually it gets the correct voltage. Okay, that means the current through it is I, so it is R, so IR. This is, here it was getting 110 volt, so here also it will get 110 volt, so IR will be 110 volt. Okay, fine. So now we know that VR equals, this is a series LR circuit clearly. So in a series LR circuit we know IR into Z. Z is R square plus the magnitude of the impedance of the circuit, omega square L square equals VR. Okay, so IR can be calculated from here. This is basically IR into R. So IR into, it is 220, so it will be half. Okay, so half is root over R square plus omega is 2 pi f, so it will be 4 pi square f square L square. It is 220, right? So R square plus 4 pi square f square L square will be 4 into 220 square. Okay, now R is 220 itself, so it is 4 into pi square is 10, f square, what is f? F is 50, so 50 square, L square is 4 into 220 square minus R is 220, so it is 220 square, so it is L square is 3 into 220 square divided by 2500, so it will be 10 to the power 5, isn't it? It will be 10 to the power 5. Okay, 10 cube, 10 square, 10 square, 10 to the power 4, 10 to the power 5. Okay, so we can get L as calculated 220 into 220 by this 10 cube into 10 square, so 10 square and this 0 is gone, so I get L square as 3 into this 484 by 1000. Okay, so it will be nearly this by 1000. Okay, so it will be 1.452. okay, so L will be nearly root 1.45, that is root 1.5. okay, so root 1.5 is nearly, it is root 15 by root 10, so root 15 is nearly 4 by root 10 is nearly 3, 4 by 3, so it is 1.3 Henry. Okay, nearly. Then let us do problem number 5. This is also a very important problem for boards. Okay, an inductor coil, a capacitor and an AC source of RMS voltage 24 volt are connected in series. When frequency of the source is varied, a maximum RMS current of 6 ampere is observed. So this series LCR circuit, right? So in series LCR circuit, okay, maximum current occurs at resonance. Okay, and at resonance obviously the circuit is resistive. Okay, so the current actually becomes VR by capital R. Okay, so VR by R, resistance only, no reactance. Okay, so it is given that IR is 6 and VR is 24. So R is 4 ohm. Okay. Now it is told the inductor coil is connected to a battery of EMF 12 volt and internal resistance 4 ohm. Okay. So actually here in this problem you have to understand this thing. So here this is inductor and resistance, okay, and this is capacitance, okay, series LCR circuit, okay. It was connected like this, okay, with this 24 volt supply. Now these two things actually, this is the inductor coil actually, okay. An inductor coil contains, a inductor coil possesses inductance as well as resistance, okay, clear, fine. There is no inductor coil in the world which does not possess any resistance, okay, clear. So this is actually the inductor coil, you have to imagine it like this, okay. So now when this inductor coil is connected to a DC source of 12 volt, so what will happen? So here I have found that R is 4 ohm, L I don't know, okay. So it is connected to a DC source 12 volt, okay. So it is told, oh, it has an internal resistance of 4 ohm, okay. So what will be the current? So in steady state this inductor behaves like a short circuit to DC, okay. So inductance will have no effect here, it is just a wear, nothing else, okay. So the resistance is, net resistance is 4 plus 4, that is 8 ohm, and EMF is given, so what will be the current? EMF by resistance, so it is 12 by 8, that is 1.5 ampere, okay, clear, okay. Now let us do problem number 11, okay. This type of problem is also very much important. I equals I0 t by tau, okay. So they asked you to calculate the RMS current for the period 0 to tau. So we know, first let us calculate the mean square current. So it is 1 by, so go to for the general definition, it is integral I squared dt by integral dt from 0 to tau, okay. So it will be I0 square by tau square t squared dt from 0 to tau, and 0 to tau dt is tau. So mean square current is I0 square by tau cube, and this will be t cube by 3, that is tau cube by 3, okay, minus 0, okay. So it is I0 square by 3. So the RMS current will be root of I square average, the mean square, root of mean square current, root mean square. So it will be I0 by root 3. Okay. Okay, now let us do problem number 7. Okay, this one is also a very important type of problem for both series LCR. Acha, series LCR. So we have an inductor of 20 millihenry a capacitor of 100 microfarad and a resistor of 50 ohm. It's connected to an AC source of 12 volt, the RMS value, and 50 hertz. So how to do this thing? See, first we have to calculate the energy dissipated. So first we have to know the average power. Okay, so the average power will be IR square R. So it will be basically R I know, but IR I have to get. So VR as I know, so in terms of VR I should write. So VR square by Z square, okay, into R. Fine. Okay. So now I can find Z, okay, because all quantities are given. So if I know Z, then I can find it. Okay. See, Z is root over R square plus this thing will be a bit, yeah, we have to do it. Okay, so it will be VR square R by R square plus omega L minus 1 by omega C square. Okay, so you have to do it. So let's calculate omega L. It is 2 pi FL. So it is 2 pi, F is 50, L is 20 by 1000. So it's gone. So it's 2 pi. Okay. So it's nearly 6 ohm. And 1 by omega C will be 1 by omega is 2 pi F C. So it is 2 pi, C is 100 microfarad, F is 50. So it will be 1 by 10 pi ten to the power 4, so 10 to the power minus 2. This 10 cube. Okay. So it will be 10 to the power, so it is 100 by pi, right? It will be 100 by pi. So it's nearly 3 by 100 is 33 ohm. Okay. So you can put it here to get average power. So VR we already know 12, so it will be 12 square into R is 50 divided by 50 square minus plus 6 minus 33 whole square. Okay, so it will be 144 into 50 by 2500 plus 27 square will be 27 into 27, so it is 729. So nearly we will get this average power as 3229. Okay, so the total energy dissipated will be this into, so it is by 3229. Okay, so the total energy dissipated will be average power into time. Time is 1000 seconds. Okay, fine. So it is nearly 70 by 37 by 3, so it is 2000 joule nearly. Okay. Okay, so let us do number 9. An inductor of inductance 100 millihenry, okay, is connected in series with a resistance and a variable capacitance with an AC source of frequency 2 kilohertz. Okay, so this is also series LCR problem. Okay, so what should be the value of capacitance so that the maximum current can be drawn into the circuit? So it's resonance in series LCR circuit. Okay, so the frequency has to be equals to 1 by root LC. Okay, so f0 is 1 by 2 pi root LC. So here L is given, so you need to calculate C. It's very easy. So it will be 1 by 4 pi square f0 square L. So just put the values and get it. 4 into 10 into f0 is 2 kilohertz. Okay, so it's 2 into 10 cube hertz. So it will be 4 into 10 to the power 6 hertz, and L is 100 millihenry, means 100 into 10 to the power minus 3, that is 0.1 Henry. Okay, put it there. So it will be 1 by 16, 7 minus 1, so 10 to the power minus 6, isn't it? So it is, if 1 by 16 is 100, that is 0.6, or 6 into 10 to the power minus 2, that is 6 into 10 to the power minus 8 farad nearly. Okay, nearly. So it will be 60 nanofarad. Okay, fine. And let us do problem number 8 as well. The dielectric strength of air is 3 into 10 to the power 6 volt per meter. A parallel plate capacitor has area 20 centimeter square and plate separation 0.1 millimeter. Find the maximum RMS voltage of an AC source which can be safely connected to this capacitor. So it will be, the RMS voltage will be like this, na, into D. So it's given 3 into 10 to the power 6 into D is 0.1 into, it's millimeter, so it's 10 to the power minus 3, so 10 to the power minus 4, so it's 300 volt, right? Okay, here in this problem number 8, it is given the dielectric strength to be 3 into 10 to the power 6 volt per meter. So actually this is the amplitude of the oscillating electric field, right? Okay, so actually this is E0. So in order to find ER will be E0 by root 2, right? Okay, so the RMS value has been asked. Okay, the RMS voltage has been asked, so it has to be, this is actually 300 volt is the peak value. Okay, so we have to divide it by root 2. So we get like 150 root 2. So 15 into 14 will be like 210 volt. Okay, the RMS value. If the peak value of the AC source was asked, then it was 300 volt. Okay, fine. Okay, now let us do this problem number 4. This type of problem is asked in the boards. It's very common. R is 300. Okay. C is LCR, series LCR circuit, 20 microfarad, and L is 1 Henry. Okay, so and frequency is 50 by pi hertz. So omega will be 2 pi f, so it will be 50 by pi, so it's 100 rad per second. Okay, so the inductive reactance will be 100 ohm, right? 100 into 1, that is 100 ohm, and the capacitive reactance will be 100 into 20 into 10 to the power minus 6, so it will be 0.5 into 10 cube, so it will be 500 ohm, right? So now the voltage, so if we need to calculate Z, the impedance will be root over R square plus XL minus XC whole square. It is 300 square plus 100 minus 500, so it will come out to be 400 square. So it will be like, so 100 square common, so it will be 100. 3 square plus 4 square will be 25. Root of 25 is 5, that is 500 ohm is the impedance of the circuit. So it's very easy. The RMS value of the source is given, the RMS value of the source is given as 50 volt, so the RMS value of current will be this 50 by 500, so it will be 0.1 ampere. So the voltage across the resistance will be IR into R, that is 0.1 into 300, that is 30 volt. The voltage across inductance will be IR into inductive reactance, so it will be 0.1, that is 10 volt, 0.1 into 100, and VC will be IR into capacitive reactance, that is it is 500, right? So it is coming out to be 50 volt. So you see, so obviously VR plus VL plus VC, it is 10 plus 30 plus 10 plus this, okay, 50, so it is 90 volt, okay, and the magnitude, okay, and the source voltage, if you call it V, this one RMS is what, 50, right? So they are not equal, okay, it is expected, this is AC, okay, here the phase factor will be introduced, okay, so obviously the sum of scalar magnitudes will not be equal like DC. It is expected that V will not be equals V, the sum of this thing, okay, fine, okay, but here the factor is this. We have already studied the phasor, so we know these voltages add like vector, okay, so it has to be this thing should hold. Let us check. Obviously it is 30 square plus 10 minus 50 square. See, this thing holds 30 square plus 40 square, so okay, so it will be 50, okay, so this thing holds, fine, clear, okay. So also they ask you the average electric field energy and the average magnetic field energy, okay, so the electric field energy is half CV square, right? So it is CVC square, so do it, half into 20 into 10 to the power minus 6 into VC is 50. All these values are RMS values, right? These values are RMS values, okay, so this is also the RMS value, okay, so it is 2500 into 10 to the power minus 5 minus 3 joule, 25 millijoule, okay, and will be half Li square, alright, so it is half L is 1 Henry and I is 0.1, so it is 0.5 into 0.01, so 5 into 10 to the power minus 3 joule, so it's 5 millijoule, okay. So this type of problems, this problem is also important, this problem is very much asked in boards. Now let us do Problem number 15. A resistance of 20 ohm is connected to a source of alternating current rated this. Find the RMS current, maximum instantaneous current in the resistor, that is the RMS current we have to find, then maximum instantaneous current, that is the amplitude, and the time taken by the current to change from its maximum value to RMS value, from amplitude to RMS. Okay, oh, fine. It's sinusoidal AC, so it will be like, it's simple, resistance is connected, so IR will be, it's very easy, VR by R, so 110 by 20, so it will be 5.5 ampere. So I0 will be IR into root 2, so 5.5 into 1.4, so it's 7.7, right, ampere. And see, we know I is I0 sine omega t, alright, so it will be, the frequency is given as 50 Hz, so omega will be 2 pi f, that is 50 into 200 pi, so you see it is, now the current becomes, say at time t, the current becomes equal to the RMS value. Okay, it is I0 sine omega t, so it is I0 by root 2, is I0 sine omega t, so it is sine pi by 4 sine omega t, so omega t becomes pi by 4, so t becomes pi by 4 omega, so it is pi by 4 into 100 pi, so it is 1 by 400 seconds, right, so t is basically 1 by 400 seconds, or you can also call it like 1 by 4 is 0.25 into 10 to the power minus 2 second. So if you want to calculate it in millisecond, then you have to multiply it by 10 cube, so it becomes 10, so 2.5 milliseconds. Okay, so it is the time during which the current changes from the maximum value, instantaneous value, amplitude to RMS.